Hi everyone. Today we're going to be talking about bounded quantifiers. Now you're probably already familiar with ordinary quantifiers, which are for all and exists. For example, we might have for all x, p of x, where p of x is a predicate in the variable x, or there exists an x such that p of x. But what if we want to restrict the domain of x? So let me show you what I mean by that. We might want to say something like for all x, r of x, where r of x is some predicate that we're insisting that x satisfies p of x. Or we might have there exists an x such that r of x and p of x. So what do these mean? Let me define them for you. What this one means, the universal one, is for all x, if r of x is satisfied, then p of x is also satisfied. And the existential one means there exists an x such that both r of x and p of x. Let me show you what I mean by these in a diagrammatic way. For the left one, the universal one, we have that these are all the x's that satisfy r of x, and outside it we have all the x's that satisfy p of x. And the point is that the x's that satisfy the r of x, they lie inside all the x's that satisfy the p of x. However, the story is a bit different on the right hand side. We have r of x is here, the x's that satisfy r, and we have p of x here. And what this bounded existential quantifier is saying is that in between, at the intersection, there exists an x. There might be more than one, we don't know. We might sometimes know, but this quantifier by itself is not mentioning anything about uniqueness. So as you can see, there is a difference between the two. One has a circle inside a circle, and the other one has two intersecting circles. Let's work with these bounded quantifiers a little bit. I want to explain them to you in terms of two applications. The first one is nested bounded quantifiers. So what happens if we have more than one of these? Let me show you an example of how to open something like that up. Let's say we have something like for all x, r of x, and then we have there exists an x such that there exists a y such that s of y, and they must satisfy p of x, y, where p is a predicate and the variables x and y. So what does this mean? How can we open this up? The technique that I like to use is substitution. We let there exists y such that s of y and p of x, y equal to q of x, because x is still free. Y is quantified, but x is still free. And so what this then becomes is for all x, r of x, q of x. And we know what the definition of this. this is equal to, for all x, if r of x, then q of x. And we can keep going through with this because now we can substitute q back in to get for all x, r of x implies, and now we have q up here. We can substitute the definition back in to get there exists a y such that s of y, p of xy. Let's open up the inner bounded existential quantifier as well. We get for all x, r of x implies there exists a y such that s of y and p of xy. As you can see, this gets ugly pretty quickly. So in general, I don't recommend opening things up like this unless you really need to understand what's happening. And I'll give you an example of when you have to really understand something and open things up, and that's the next point, which is how to negate bounded quantifiers. Now, I'll show you two examples. One is negating the universal one, and the other one is negating the existential one. Let's say we want to negate for all x, r of x, p of x. Let's turn this into the implication. So we have not for all x, r of x implies p of x. And just so that we know exactly what we're doing, we're going to turn this into a disjunction, which is for all x, we have not r of x or p of x. And now we can use De Morgan's law for quantifiers to negate this. This is there exists an x such that r of x and not p of x. And we can pull the r of x out now. This is equal to there exists an x such that r of x not p of x. This is a little bit amazing because the r of x was up here and the r of x is down here, and we just negated everything else the way we normally would with De Morgan, because normally we would say not for all x p of x is equal to there exists an x not p of x, and that's exactly what we did, and we took out the r of x and we popped it back in. Let's see if the same thing happens if we do a negation of a existential bounded quantifier. Let's try it out. We have not there exists an x such that r of x p of x, and we'll open it up to get not there exists an x such that r of x and p of x. And we know what to do here because we can just apply De Morgan's law to flip the e into an a. So we get for all x not r of x or not p of x. The trick here is that the not r of x or, that part is an implication in disguise. So we can write this as for all x, r of x implies not p of x. And by the definition of a bounded universal quantifier, we can pull the r of x out to get for all x, r of x, p of x. Now notice we had an r of x up here, we had an r of x down here, and it was just like applying De Morgan's laws while ignoring the r of x, because if we had not there exists x such that p of x, then we could just negate this by saying for all x not p of x, and that should have been a not up here. There we go. Hopefully you notice that. And that is how we negate bounded quantifiers. So let me go back to the beginning and just recap what we did. We had the definition of bounded quantifiers. We looked at a visualization. We showed an example of how to open up nested bounded quantifiers. And finally, we showed a variation of De Morgan's laws for bounded quantifiers, how to negate them. Hopefully you learned something new, and until next time, see you.